He's going to talk about his work with Eric Darv at Stanford on ADCME. I can never get that right. So take it away.
Okay, sure. Thank you. Today I would like to talk about my work on ADCME MPI, which is for distributed machine learning for computational engineering. My talk will be divided into 3 parts. In the first part, I will give a short introduction to what inverse modeling is. And in the second part, I will describe the technique of automatic differentiation. And in the last part, I will introduce the distributed computing technique in ADCME for computational engineering. So in computational engineering, we are basically solving 2 types of problems. The first type of problem is called forward problem. In this type of problems, we have the physical laws, we load the parameters in the physical laws, and then we can do numerical simulations and get predictions of observations. And nowadays, we have a lot of data from sensors or experiments, and we want to solve inverse problem to have a better physical model. In these problems, we know the physical laws, for example, the conservation laws, but we do not know some parameters in the physical laws or some unknown functions, for example, the constitutive relations of a material. And we have the observations from experiments or sensors or even simulations. And we want to use these observations to calibrate the parameters in the physical laws. This is called the inverse problem. And one way to solve the inverse problem is to formulate the problem as a PD constraint optimization problem. Here, I present a very abstract form of the PD constraint problem. And LH here is the loss function, which measures the discrepancy between the prediction, UH is the state variable we're interested here, and also the observation. For example, LH could be a quadratic loss function between a state variable and observations. And FH here is a PD constraint. It can be a discretized form of a system of partial differential equations. And the theta here is the quantity of interest. And UH, as I said, is a state variable. For example, if we are solving a Poisson's equation and this Poisson's equation is discretized using, for example, a finite element method, we may have a form like this. And the theta might be the coefficient in the Poisson's equation, for example, the diffusivity coefficient. And we will, and this is the linear system to solve. And once we solve the linear system, we can get the state variable. And UOBS will be the observation of our state variable. And what I just described is the so-called parameter inverse problem, where the unknown is just a parameter. And what is more interesting is the so-called function inverse problem, where the unknown is a function. Here, I just replace theta with the unknown function f. And this type of problem has a lot of applications in different disciplines. For example, in dynamical systems, people try to find the so-called Koopman operator. And in solid mechanics, people want to construct the constitutive relations from experiment data. And in fluid dynamics, people want to find a turbulent closure to describe the turbulent system. And this type of problem has a very challenging issue here. That is, the unknown parameter or unknown function space is infinite dimensional. So that brings some difficulty to our solving technique. And our approach here is to propose a deep neural network-based data-driven modeling technique here. And this unknown function is replaced by a deep neural network. So we reduce the original function inverse problem into a parameter inverse problem, where the unknown is the neural network weights and biases. And in our approach, instead of just like most common approaches, where you incorporate this PD constraint as a penalty term in the last function, we solve this constraint directly using, for example, finite element solver or finite difference solver, and get this UH. And you can assume that this UH is a function of theta, but we cannot calculate this function analytically in most cases. We can only solve UH from this equation to get a function of theta. And then we can just plug this UH into the last function. Then we reduce the original constraint optimization problem into an unconstrained one. So we can, like this one, So we can apply a gradient, unconstrained gradient descent optimizer to solve this problem. The motivation for using a deep neural network here is that for many cases, this F might be a high dimensional space. Some alternative approaches, such as using linear compilation of basis functions, they have a greater difficulty when the dimension is very high, because you need a very fine mesh in high dimensional space that would cause cursive dimensionality. And this is a summary of our approach. So we have an unconstrained optimization problem. We first reduce it. We have a constrained optimization problem. We first reduce it to an unconstrained one, and then we perform gradient descent. And yeah, if you have some parameters here, you have a PDE, then you can do some simulations and get observations. And then you compare with the observed data, and then you can calculate the loss function. Then you calculate the gradient, and then close this loop. So let's go into more technical details of this approach. As I said, what we need to do is to calculate the gradient of the loss function. But how do we do that? And this is this technique arises from the observation of the deep learning techniques. In deep learning, we usually have many deep neural networks, which are composed of layers of neural networks. And if you compare that with a numerical solver in scientific computing, you will find many similar patterns here. For example, in deep neural networks, you have layers by layers, and when you do forward inference, you just calculate the activation values layer by layer. And in a numerical PDE solver, for example, a time-dependent solver, you have time step by time step. When you calculate the solutions of the PDE, you just propagate the solution time step by time step. And when you calculate the gradients of a deep neural network, you just backpropagate the gradient from last layer to the first layer. And in numerical PDEs, when you calculate the so-called joint variables, you just calculate the gradients from the last time step to the first time step. So you have a lot of common patterns here. And actually, you can show mathematically that the so-called backpropagation in deep neural networks and the discrete joint state method in scientific computing are actually the same method. They fall under the umbrella of reverse mode automatic differentiation. Based on this observation, then we can leverage the deep learning tools for solving problems in scientific computing. And the key here is to express the numerical schemes in an AD language, which is the computational graph. So basically, we can construct a numerical solver as a computational graph. For example, in this plot, each node can be a numerical operator. For example, a linear solver or a Newton-Raphson solver, and each edge represents the state variable. For example, the velocity or some fluid potential or some other state variables. So this is a representation of 3 time steps in a numerical solver. And once you construct a computational graph for your numerical solver, then you can combine it with your deep neural network, and then you can do the gradient calculation very easily using automatic differentiation. So you do not have to derive the gradients by hand, and everything is done automatically using software. And this is where ADCME comes in. So we built ADCME, the software that is for automatic differentiation for computational engineering. And the backend is TensorFlow, which is used for automatic differentiation and computational graph optimization. So the basic idea is that we decompose the computation of numerical solver and deep neural networks as a computational graph, which consists of nodes and these edges. And each node can be, for example, the linear transformation or activation or linear solver. And also you can incorporate your custom operators, which can be a CUDA kernel or Fortran kernel or any legacy code. And TensorFlow is used for deep learning, and it is very good at many machine learning techniques and machine learning problems. However, it lacks some capabilities for computational engineering. For example, in computational engineering, we need numerical schemes, we need linear solvers, we also need MPI operations, which I will describe later. and we also need many other custom optimizers, for example, BFGS, IPOps, and NLP. And those capabilities are not well supported by the deep learning framework. So this is where ADCME contributes to for this computational engineering. And how does ADCME work? And this is actually this is a representation of the workflow. So you write your numerical scheme on a high level. So here at this level, you do not need to think about the computational graph, because the ADCME will automatically construct the computational graph from your codes. And this code is actually these codes are actually very similar to MATLAB codes, or are very natural, and you do not have to think about the low level details. And the ADCME transforms your code into a computational graph, and the computational graph is fed to TensorFlow, and the TensorFlow does some computational graph optimization, and then dedicated to a heterogeneous computing environment. So you can run the code on CPUs, GPUs, TPUs, and any computing frameworks that are supported by TensorFlow. And this enters, and then we enter our last part, which is for distributed computing in computational engineering. So in deep learning, when we talk about distributed computing, we usually think of a list model. So we have this loss function, which is a summation of losses of different parts. And the key here is that we can decompose the summation of the loss functions into different batches, and those batches are independent. So a natural way for distributed computing of deep learning loss function is that we can compute a loss function, a part of the loss function on each machine, and then compute the gradients, and then we have some leader loads to aggregate the gradients and update the parameters. And in some cases, the parameters space is very large. For example, you have 1 billion parameters, and these 1 billion parameters may not fit onto a single machine. Then you need to use a distributed system to store those parameters. And this comes the so-called parameter server model. And yeah, those techniques are very common in deep learning. However, if we think about the computational engineering, the patterns are quite different. Let's think about time-dependent PDE. So you split your state variable onto P machines, and then you have a system of partial differential equations. And in this, in each time step, you need to solve a linear system where let's say theta is a coefficient matrix, and you have to solve this, for example, let's ui from ui minus 1. And to solve this system, you have all the parameters, all the state variables on each partition will interact with each other. For example, you need a MPI enabled numerical solver, and this is the computational graph for this numerical scheme. So you can see for each time step, you have to communicate the data between different machines. And this is quite different from deep learning, where you own all the computations can be done independently on a single machine, and then you finally just do one step gradient aggregation. So this is how we solve this problem in ADCME MPI, and actually the solution is quite elegant. So we treat the MPI operations as the load in the computational graph, and this computational node are only in charge of the data communication and also the gradient backpropagation of the MPI operation. And then, and because of this elegant solution, the ADCME MPI is very transparent to users. So users does not need to think about the backend, and actually users can adapt their single processor code to distributed one very easily. Yeah, this is an example to illustrate how it works in ADCME. For example, if you want to calculate this loss function in a distributed system, yeah, and this is the ADCME code. So actually, all we need to do is to add 2 lines of code. This is we need to broadcast this data onto different machines, and then when we do the summation of the loss function, we only need to do MPI sum instead of the typical sum function. And then we can just convert this serial code into distributed computing code. Finally, I would like to present some results. Actually, in this model, we can convert a serial constant optimization code into optimizer into a distributed optimizer very easily. But I do not want to go into details of that. This is a benchmark for our framework. And here we solve a Poisson's equation where the unknown function is replaced by a deep neural network. And you can see here, this coefficient is a deep neural network, and the weight and basis is theta. And we want to calibrate this neural network weight and basis. And if we want to apply our framework, we need to first solve this equation, and we use algebraic multigrid method provided by Hyper, which is software for distributed algebraic multigrid method solver. And then after solving this equation, we plug the solution into the last function, calculate the last function, and do the gradient back propagation. And this is actually an illustration of the computational graph for this plot, for this equation. And actually, we split the solutions into different patches. And here, and here is the result. And in this results, I show the forward computation, which is shown in red, and the backward computation, which is shown in blue. And the first row corresponds to 1 core per MPI processor, and the second row corresponds to 4 cores per processor. Because TensorFlow is a multi-threaded program, so if we provided more cores, it can be more computational efficient. And we show the runtime here, and we also show the overhead introduced by ADCME compared to Hyper, because most of the time is spent in Hyper. So the appropriate metric to measure the performance of ADCME is through this overhead. You can see this overhead is very small compared to the total time, which means our framework is quite efficient. And that reaches the end of my talk. And if you are more interested in technical details, you can refer to this documentation. And finally, I would like to reintroduce ADCME, which is a framework for doing scientific computing, inverse modeling that combines data, deep neural networks, conservation nodes, and numerical schemes. And we also have many other packages that are developed based on ADCME for different disciplines. For example, the ADFM is a finite element library for inverse modeling that facilitates users to write a computational graph based numerical solver very easily. And also, and for example, ADCME is for a general framework for seismic inversion. That's the end of my talk, and I would be very happy to take any questions.
Thank you very much, Kailai. Anybody have any questions, please enter them in the chat, or just go ahead and ask them. And just as a heads up there, we're going to leave the sessions, the breakout sessions will be open for 15 minutes after the talks for people to, if they want to discuss or any of the questions for any of the speakers or anything else that comes up. I guess so the task-based parallelism, you're doing that, is that only done at kind of the TensorFlow level, or are you also trying to do some task-based parallelism kind of at the ADCME computational graph level?
Actually, what we are doing is to add the custom operators to TensorFlow. So there are some actual operators in TensorFlow, so that those operators can do MPI communications. That's our approach to that.
Okay, so but is there any sort of for load balancing, or is there any kind of infrastructure for that to look kind of at your sort of at the overall ADCME computational graph and try and do some of that balancing on the fly, or is that more straight domain-based parallelism right now?
Right now, we do not have like automatic load balancing. That's still that users still need to take care of that themselves. because the users, right now it's just providing users with like MPI operators. So users can say, oh, I want to pronounce this part. So then we just add, call an extra function at this part.
Okay. And I have one more question about this. Just how much work is it to like, say the hyper or the mumps, like existing kind of higher, like, you know, legacy, if you want to add tools, if you want to add them as a node in the framework, how hard is that to do?
It's actually not very hard right now. Yeah, because it's like the workflow is like you compile your legacy code as a shared library, and then you just use ADCME to link to your library. Yeah, that's also how TensorFlow incorporates custom operators.